Okay, begin week 10, and let's see where we've come from and where we're going for the rest of the semester. So we did 3 weeks of kinematics, motion, one-dimensional, two-dimensional, learning about vectors, and we're going to revisit all that this week. Then we spent 2 weeks talking about force and the relationship between force and motion. Then we talked about energy and work for 2 weeks and the relationship that that has to all of this. And we just did momentum. And for all of this, we were talking about objects moving through space. And now we're going to repeat this for spinning objects. We're going to do rotational kinematics, rotational force, rotational energy and work. We won't actually do rotational momentum because we'll run out of time. So that's where we begin this week with rotational kinematics. And I'll show you how that relates to what we previously learned, especially in weeks 2, 3, and 4. But before we start that, keep in mind, learning is an active process. So you're practicing and you're repeating. That's what's good about the MOPS. There's a lot of repetition. But for the rest of the semester, there'll be, well, except for one exception, there'll be no more MOPS. So you want to do the assignments, you want to do the labs, you want to do them carefully, and you want to try and actively learn the new material in connection to the old material. So just like learning a language or learning music skills or learning any subject area, what we have already learned is an important foundation for what we're going to continue to learn. And the more you can connect and integrate all that knowledge, the better you'll understand and be able to remember concepts and methods of problem solving. Okay, so let's begin this week's subject of rotational kinematics. So just to make sure that everything we talk about is real in physical space, we want to look at some familiar rotating objects like a bicycle wheel. So if it's on the bike, it spins and it moves through space. But if it's sitting here in this picture, it's just spinning. It's not going anywhere. It's not changing its position in space. So how do we describe its motion? And the merry-go-round goes round and around and around. The merry-go-round doesn't move around in space. It doesn't change its position. It just spins. So we want to describe that. However, the person on the merry-go-round horse spins and does cover space. So there is a relationship. If you have an object on a spinning disc, it will have rotational motion and linear motion. It does move through space. So how we relate those two things is also part of this week's study. So if we were in real meetings, if we were in school on campus, the lab and the kind of demonstrations I would be showing you in the class would involve these two apparatuses. This one stands maybe 3 feet tall, and it's kind of like a bicycle wheel. It's a central hub that has 4 rods that screw into it, and these adjustable masses that can be moved along the rod. So this is like a spoked apparatus that spins where the axis is horizontal, and so it's spinning in the vertical plane, kind of like a bicycle wheel. The other one is we have a rotating platform that holds a disc or a hoop, and on the base of the platform is a smaller disc that we wrap a string around. We put it over a pulley, either a single pulley to the ground, or here it shows a double pulley. And as the mass falls, the mass will accelerate, of course, much slower than if we just dropped it, right? But it will accelerate. And as it accelerates, the spinning disc will spin faster and faster and faster and accelerate. And so most of the problems in the assignment are related to an apparatus very similar to this that we actually use in class when we're in class. And continuing, just to keep this further from being too abstract for you, since we're just remote, here's a picture of the apparatus against the blackboard, and you can see that the apparatus itself, that hub, has several discs of different diameters that we can wrap a string around. And when we wrap the string around and put a weight on it, the weight is going to fall and accelerate, and the rotating apparatus is going to accelerate this way. And we can adjust the weight that we put on there, we can adjust the place that we put it, and we'll get different kinds of acceleration. So this is a little more detail on this apparatus that we will use in some of the problems that you'll see in the assignment. And the other apparatus, the rotating platform apparatus, has, you'll see diagrams like this, which is basically that apparatus in a diagram form. You can see the string that's going to unwrap as the weight falls, and it may just be a disc, or it may be a disc with masses on it. And again, if a mass is on there, we can talk about its rotational speed and its linear speed. So we have to be able to relate those two motions. You'll see this when you get to the assignment. Here's another diagram of one of these vertical axis, right? It has a vertical axis and it spins in the horizontal plane. And in this case, there's a band. This is a band, a horizontal band that sticks out, and a photo gate. So you see when that black tape goes through the photo gate, it can measure how long it takes to go through the photo gate. This is something, again, that we do in lab, but we're not able to do it. And so you'll see this very diagram as part of the assignment. And so this sticks out from the skirt. This is a disc, and this is a rotating platform type apparatus. And finally, one last variation. If you see this platform, you can see the platform here. We have a bar. This is another actual device apparatus that we use in lab. And that bar is screwed to the rotating platform, and two large masses are placed on the bar. And so we can wrap the string around here, go over a pulley, have it fall, and this thing will spin, and this whole bar mass arrangement will spin. This will show up, I think, in this assignment and in next week's assignment. So just so you have a good sense, because you're not in class to actually see these things, a good sense of the best you can of what these apparatuses actually look like. So before we jump into rotational motion, let's just review what we learned weeks ago about linear motion. There were three concepts: displacement, velocity, and acceleration. Displacement means, can you say it? Change in position. So the change in position is the final position minus the initial position. So this is how we get displacement, and it is a vector, and it has a magnitude and a direction. This, of course, is just for a displacement along the x-axis, but we know how to handle that if it's in 2 dimensions. So we can talk about position, and we can talk about change in position. That's velocity. So if we take the change in position, the distance, divided by the time, we get an average velocity. And remember, if the velocity is constant, the average velocity is the velocity at any instant. But in general, things don't have constant velocities. So as the velocity changes, the instantaneous velocity will be different from the average velocity. Like you take a trip in your car and your instantaneous velocity is your speedometer reading, but your average velocity over the trip won't tell you very much about what it was at any particular instant. So the way we define instantaneous velocity, this is important. We define it by taking an average velocity over a very small interval. And this is a mathematical way of saying that in order to get the velocity at a particular instant, that distance over time interval has to be as small as possible. And mathematically, it's possible to have that infinitely small. That's calculus. That's the concept of calculus. And so the definition in a one-dimensional problem of instantaneous velocity is the derivative of x with respect to time. And that's what the derivative means. It's an infinitesimal ratio of two quantities. And the same thing applies to acceleration. So we want to know how is the thing moving through space and how is the velocity changing. So the average velocity will be the change in velocity over time. And for most of the cases we studied, acceleration was constant. So the average and the instantaneous was the same. But if we had an oscillating pendulum, the acceleration would be changing, and we would have to define instantaneous acceleration in the same way. It would be the change in velocity over time when that ratio became infinitely small, and that is the derivative of the velocity vector with respect to time, which you should now know, even if you're in Calc 1, that is the derivative of a derivative, so it's the second derivative of the position vector with respect to time. So these are our definitions back in week 2, and now let's apply these same ideas to rotational motion. So now let's discuss displacement, velocity, and acceleration in the rotational space or rotational world. And so we can call it rotational displacement, but a more common term is angular displacement. We can call it rotational velocity or angular velocity. We can call it rotational acceleration or angular acceleration. Both those terms are widely used. And if we go to our disk, it looks stationary, right? But supposing I spin this a little bit, and now you look at it, you can't tell that it's spun, right? And I spin it a little more because it hasn't moved through space. So we need to put a reference point on it. Let's put a radius on it. And then when we spin it, if I spin it, say, through a quarter turn, then we'll see the line up here. And we can now describe its displacement, how much it's moved in its circular motion, in its rotational motion. And there's 3 ways we can do it. We can say it moved a quarter turn, or a quarter of a rotation. Or we can say it moved 90 degrees. Or we can say it moved pi over 2 radians. What does that mean? Well, if you're familiar with radians, good, you know what it means. If you're not, let me explain. So starting with a new figure, when we're talking about how far something moved by spinning, a rotation is a natural unit, right? 1 rotation. So describing a quarter rotation, a third of a rotation, 2 rotations is a very natural way of describing things. 360 degrees is kind of a man-made artificial system that we know and we can use. So if a thing went a half a rotation, that would be 180 degrees. But another commonly used natural unit for measuring angles is to take the radius of the circle and wrap it around the edge of the circle. So if, say, this radius is 10 centimeters, then I draw an arc length. This is called an arc length, an arc along the circle. And I go 10 centimeters along the arc. And so S is the symbol we use for arc length. r is the radius, and so the angle in radians is whatever the arc length is over the radius. So if the arc length is equal to the radius, that will be 1 radian, and as you'll see later, that turns out to be 57.3 something degrees. So if I go around the whole circle, right, the circumference of the circle, so here's our definition. What's the angle in radians for a complete rotation? So one rotation is 360 degrees. How many radians? So that angle for one rotation has to be the arc length over the radius. But the arc length of a complete circle is its circumference. So it's 2 pi r, that's the s, divided by r. And there's where, I hope you understand this, that's where the 2 pi radians comes from. But 2 pi is a number, right? It's 6.28 something. So what does that mean? I want you to understand what that means. Let me show you what it means. I take the radius, 10 centimeters, and I go 10 centimeters. Then I go another 10 centimeters. Then I go another 10 centimeters. Then I go a fourth, a fifth, and a sixth, and I end up about here. Why? Because it takes 6.28 or 2 pi radiuses to complete the circle. So we often use, you'll see as we do the problems, we'll often leave the pi as pi. So 2 pi is 6.28 plus some other digits. We can call it 2 pi or you can call it 6.28. And so that's the way in which we convert angles, radians, and rotations. One rotation is 360 degrees is 2 pi radians. So those are our conversion factors. One rotation, 360 degrees, 2 pi radians. And you see that we're going to use those a lot when we calculate angular displacements or rotational displacements. Okay, so from there it's a short step, I think, to defining rotational or angular velocity and rotational angular acceleration. And you'll see this parallels exactly what we did back in week 2 when we defined velocity and acceleration. So angular displacement is measured in rotations or radians, not usually degrees, usually rotations and radians. And so if we take the displacement over the time, that gives us the speed at which something is rotating. So if it's doing 1 rotation every second, it's doing 2 pi radians every second, it's doing 360 degrees every second. And so that's how we define omega, this curly W. People call it W, but it's omega. It's lowercase Greek letter omega, and its omega average is the change in angular displacement, right? Oh, I didn't mention we use the symbol theta for angular displacement. So delta, the change in angular position, is called delta theta. So if we take that over time, we get the average velocity. And similarly, if we want to get the instantaneous velocity, right, if it's constant, no problem. But if it's speeding up as it rotates, then we have to talk about how the angular velocity is changing over time, and that's acceleration. And so at any instant, the way we define instantaneous angular velocity or rotational velocity is the limit as the ratio of delta theta delta t goes to 0, or the derivative of delta theta delta t. And acceleration is just the rate at which the speed or angular velocity is changing. And so this gives us the average. Similarly, this gives us the instantaneous, and we can, the ultimate best definition is the calculus definition for that. So these are our definitions. This forms what later, in the later video, will be called group 1 of our kinematics equations. The equations that define all the rotational or angular quantities. So from these, especially using this one and this one, we can derive, as we did previously, 4 working equations of motion, and I'm going to show you those now. Okay, here are our working 4 kinematics equations. So this is only true for the case where alpha, the angular acceleration, is constant. That means the velocity is changing, but it's changing at a steady rate. And so if alpha is constant, then the alpha is instantaneous and average is the same. So here's alpha average. And we simply rewrite it and get this equation, which is our first of our kinematics equations, and it exactly parallels, if you go back to week 2, the first of our kinematics equations back in week 2. Then if we take, with a constant alpha, we can write that omega average is the final plus the initial divided by 2. That gives us the average. Whoops. The t shouldn't have been there. And then we take the equation, let me just write that. So stepping back to our definition of the average angular speed and relating it to this. So the average angular speed by definition is this. If we rewrite it, we get delta theta equals the average omega times the time. And if I bring that up here, and I substitute this version of omega average, we get this equation. And this equation is on our list of kinematics equations, what we call number 2. And then if we take this equation and if we substitute, omega final is equal to this. So if we take this omega final and substitute it in here and do the algebra, not difficult, you can do it, we end up with this equation. The omega final gets eliminated by substitution, and this is our kinematics equation number 3. Exactly parallels our previous one. And then if we take and we solve this, if we solve this for t, whoops, if we solve this equation for t and substitute that in here and multiply it out, we eliminate t, creating this 4th useful and convenient kinematics equation, similar to what we've seen previously. So these are our quote-unquote group 2. Later on I'll talk about group 1, group 2, and group 3. Group 1 being the definitions, group 2 being this working set of kinematics equations that we solve problems with. And so finally, what is group 3? So our group 3 equations are the equations that relate angular quantities with linear quantities. What am I talking about? Supposing this merry-go-round is taking 2 seconds to go around. Then it's going a half a rotation, 0.5 rotations per second, or pi, 3.14 radians per second, 180 degrees, right? But the people on the platform, so I put a person here, there's the person on the horse, there's a person standing at the edge. This person isn't moving, doesn't go as far, and isn't moving as fast as the person in the middle. And the person that's moving the furthest, so the omega, this person goes a half a rotation a second. The person on the horse goes a half a rotation a second. This person goes a half a rotation. But their displacement, their velocity, and if there is an acceleration in the linear realm are all different. So we need equations to relate those quantities, and that's group 3. I'm going to show you that now. Okay, one comment if you're still here. I know this is 25 minutes into this video, 26 minutes. There's a lot of information. If you haven't done the assignment, a lot of it's, your head's going to be swimming. So just, you've seen it, you need to do the assignment, you need to put it to work. And after you've done the assignment in lab, I really recommend you come back and watch the video one more time because it synthesizes, pulls together, connects all the information we know about linear and angular quantities. So we start here with our definition of the radian. It's the arc length over the radius. So if we want to know how far this person goes when it goes through a half a rotation, right? That's the arc length. And so the angle is the radius, is the arc length over the radius. Like a half a turn is 3.14 radii, right? So the distance the person moves, we simply rewrite this equation. The distance that this person will travel will be the pi radians per second times the radius. And a person with a different radius, a smaller radius, travels a smaller distance, and the person out on the edge with the biggest radius travels the biggest distance. So although they all have the same theta, they don't have the same distance, arc length, or distance that they travel. Same way with the velocity. This person, they all go this distance in the same time, right? 1 second to do a half a rotation. So their velocity is going to vary. And you'll see this written as VT. It means tangential. Because a person at this point is always, as someone moves in a circle, they're always moving tangent to the circle. So that T means tangential. The tangential velocity is the angular velocity times the radius. So once again, the person with the small radius has the smaller tangential velocity, and the person with the biggest radius has the biggest tangential velocity. And if the thing is accelerating, either positive or negative, then the linear acceleration of each person can be gotten in the same way, the tangential acceleration, right? If this person is speeding up, it will simply be the angular acceleration times r. Once again, the person closest to the center has the least acceleration, and the person far out the most acceleration. But one last complication, that's the tangential acceleration. So as this person moves around, if the velocity is constant, then the tangential acceleration, the tangential velocity will be constant, and there'll be no tangential acceleration. But we know from what we studied back in week 6 that in order to move in a circle, there has to be a centripetal force on this person, in this case friction, keeping the person in the circle. So you may remember that centripetal acceleration, even for the person moving at a constant speed, has a centripetal acceleration. And remember, that was v squared over r. And so the v that we're talking about is the tangential velocity. But using this equation, we can rewrite this and get a new form. So we can get the centripetal acceleration from the tangential velocity or from the angular velocity. So keep in mind that there are two kinds of accelerations that a person has when they're moving in a circle. And so this group of equations is our kinematics group 3 equations, and they're called the conversion equations, converting from linear to angular or angular to linear. So those are all the definitions and concepts that you need to do the assignment in the lab. And there are videos actually to help you specifically with those. But I think it's a good idea after you've done those to come back and rewatch the video just so you can synthesize all this information and it's well, remember the word integrated, into your knowledge base. Okay, done.